Last time we began our exploration of gravity with Isaac Newton and the famous story of the apple. This time, let's start with a more extreme example of free fall. In 2012, an Austrian adventurer named Felix Baumgartner did something extraordinary. He rode a balloon to an altitude of 39 kilometers, more than 24 miles above the ground. Then he opened the door of his gondola and jumped out. Baumgartner fell for more than 4 minutes before he opened his parachute. It was the highest skydive in history, breaking a record more than 50 years old. It was a rather dramatic experiment in gravity. Now, some of the most important insights about gravity and about mechanics, the science of force and motion, a subject of extreme interest to Felix Baumgartner in his jump, some of those insights actually predate Newton's work by more than half a century. Indeed, these original basic discoveries were not only the inspiration for Newton, but also for Einstein. If Isaac Newton was the father of mechanics, then the grandfather of mechanics was Galileo Galilei. Galileo is such an iconic figure. So much has been said and written about him, it is hard to know what to add. He had a keen mind and a quick wit. He was a superb scientist, and he was a delightful writer. He was a pivotal figure in the history of science. Galileo was a child of the Italian Renaissance. He was born in 1564, and he grew up in Pisa, the son of a famous musician and composer named Vincenzo Galilei. Vincenzo was himself a fascinating fellow. He was a pioneer in musical theory. Galileo, I think, inherited several characteristics from his father. First, a bent for mathematics. The music of the day was highly mathematical in its structure. Second, I think Galileo inherited a skill in intellectual controversy. Vincenzo was involved in great debates about musical style. And third, I think Galileo inherited a penchant for experiment. Now, that's a strange thing to say about a musician, but by experiment, Vincenzo discovered the mathematical relation between the tension in a string and the note that it plays when you pluck it, itself a significant discovery in the physics of sound. I think that from the musical training that he got from his father, Galileo developed a special appreciation for the role of time and rhythm in natural phenomena. We may say in Galileo's case that the apple does not fall far from the tree. Galileo was a student at the University of Pisa. His father wanted him to be a physician, but his interests and talents lay elsewhere. He studied mathematics and natural philosophy. The young Galileo also showed himself to be a shrewd observer of the natural world. So, at age 17, he was attending Mass at the cathedral in Pisa, and he observed a lamp hanging by a chain from the ceiling, and the lamp was swinging back and forth, and slowly the swings became less. And Galileo realized the same time is required for a long swing and a short swing. So Galileo rushes home and does some experiments. And the swing period of a pendulum does depend on the length of a pendulum, but not the length of its swing arc, if that is not too large. And it does not depend on the mass of the pendulum, even though it is the pendulum's weight that causes it to swing. So Galileo began to think deeply about the science of motion. In his 20s, Galileo became a university professor, first in Pisa and then in Padua in the Republic of Venice. And later, he became the court mathematician to the Grand Duke of Tuscany in Florence. Now, not long ago, I had occasion to visit the Museo Galileo in Florence. It's a fascinating place. And there, I came to appreciate a key aspect of Galileo. He was interested both in theory and in practical things. He spent time with craftsmen, architects, engineers. He was something of a tinkerer himself, and this gave him a sound practical knowledge of how things really work. Lenses, machines, cannons, buildings, ships. It also encouraged his impulse to investigate the world through careful experiment and observation. Why is Galileo famous? Well, there are many reasons. For instance, he was the inventor of the astronomical telescope, and with this, he made revolutionary discoveries about the heavens. Galileo became a champion of the radical theory of Nicholas Copernicus, that the Earth and other planets move around the sun. And many of Galileo's discoveries and writings supported this theory. And this led to his conflict with the church authorities of his day. But just as important were Galileo's contributions to physics, in particular, 3 epoch-making discoveries about motion, the foundation of everything that came later in all of physics. So here is Galileo's first great discovery, the principle of inertia. So here's the old idea, due to Aristotle and still believed 2,000 years later in Galileo's day. Objects on Earth are naturally at rest. And so if something is moving, there must be an outside influence. If you remove the influence, the object comes to rest. So the thing that needs explanation in this view, the thing that we must give a cause for, is velocity. Well, what is velocity? It's the rate of change of position. So suppose you are moving along a road, and we let x represent your position, that is to say, measured from some point on the road, so many meters east of that point. As you move, in a small amount of time, delta t, you change position by delta x. That Greek letter delta means how much something has changed, and it could be positive or negative. And the velocity v equals delta x divided by delta t. So let's consider an example. Suppose at t equal to 2 seconds, we are at x equal to 12 meters. And then later at t equal to 4 seconds, we are at x equal to 6 meters. So our velocity would be minus 6 meters divided by 2 seconds, which is minus 3 meters per second. That minus sign indicates that we're moving in the negative direction. Aristotle says that an object's velocity is naturally 0. But if we keep pushing it, it can continue to move at a speed that is not 0. Galileo has a very different idea. He says that objects are not naturally at rest. In the absence of an outside influence, an object at rest does remain at rest, velocity 0, but an object in motion also remains in motion at a constant velocity in a straight line. And inertia is this tendency of bodies to maintain a constant velocity, either a 0 velocity or otherwise. So according to Galileo, what requires a cause is not velocity, but acceleration. Acceleration is the rate of change of velocity. And as an equation, that would be a, representing acceleration, equals delta v divided by delta t. And any change in velocity counts as acceleration, speeding up, slowing down, or changing direction. So why do objects in everyday life slow down if they have this property of inertia? And Galileo says it's friction, it's air resistance, it's some outside influence. So imagine a ball on a flat table. You roll it and it comes to rest. Now reduce the friction. Use a smoother ball, a smoother table. Use a heavy ball to reduce the effect of air resistance. Now the ball will roll much farther before slowing to rest. So if we imagine an ideal ball with no friction, it would roll forever in agreement with the principle of inertia. Galileo's second discovery is a discovery about gravity, about how objects near the Earth fall downward. Free fall means the motion of a body under the influence of only gravity. And here's the old idea, once again due to Aristotle. Earthly objects naturally seek the center of the Earth, which is the center of the cosmos in the old geocentric view. More massive objects have a stronger tendency to do this, so more massive objects fall more quickly than less massive ones. For about 2,000 years, Aristotle and his followers regarded all this as completely obvious. Now, they did understand that an object increases its speed as it falls, but according to what rule? Well, opinions were divided. One idea was that an object that falls twice as far ends up going twice as fast. But Galileo found that this is all wrong. He discovers, first, that a freely falling object falls with a constant acceleration, and second, that all objects fall with exactly the same acceleration. We might call this pair of facts the law of free fall. So, what do I mean by constant acceleration? In constant acceleration, as you fall, your velocity increases with time. As an equation, we'd write that v equals a times t, where v is the falling velocity, a is the acceleration, which remains the same, and t is the time since you started falling. So for freely falling objects near the Earth, a is about 10 meters per second squared. And as time passes, as t in our equation increases, your velocity, v, becomes greater and greater. And the acceleration a tells us how much faster you go each second. So that tells us how fast you fall, but how far do you fall? Remember, each second you fall faster, so you cover more distance. So here is Galileo's formula for the distance covered during constant acceleration. X equals 1/2 times a times t squared, where x is the distance fallen, and a is the acceleration, and t is the time since you started falling. Well, we've written down a couple of equations. Let me say something about them. An equation is not just a handy formula for working homework problems. That is useful, and we will occasionally use them for that. But equations are much more. They express meaning, a lot of information in a small package. Equations are the haiku poetry of physics, an elegant idea crystallized in a few symbols. And equations are also very useful tools for reasoning. If you actually read the books of the early pioneers of mechanics, Galileo and Newton in particular, you will find surprisingly few algebraic equations. They liked to express their ideas in words, geometric diagrams, and proportions. They tended to write in the style of a geometry book, like Euclid's Elements. And truth to tell, it is sometimes hard to figure out exactly what they are saying. Equations, believe it or not, can be easier. We will not depend too much on the equations. This is nothing like a graduate level course on gravitational physics. It will be possible to follow along just by skipping all the math. But that would be a little like attending the symphony, but hearing only half the music. So I encourage you to invest a little time and effort to hear the rest. In the case of the equations of uniformly accelerated motion, there is a lovely way to appreciate their meaning more fully. This is an old demonstration that I saw in the Museo Galileo. Though Galileo himself did not build it, it is based on his writings, and it shows how he figured out accelerated motion. In the apparatus, a ball rolls down an inclined track. This was one of Galileo's experimental tricks. The free fall of a body was simply too quick for him to do measurements, and anyway, he had no very precise way to measure short periods of time. The ball on the sloping track still accelerates uniformly, Galileo realizes, but with a much lower acceleration. So spaced along the track are several hoops that the ball rolls through, and on each hoop is mounted a little bell. the ball rings each bell as it passes. Now, the hoops are not evenly spaced. Numerically, the distance from the starting point to each hoop is a series of squares: 1 unit, 4 units, 9 units, 16 units, and so on. The spaces between the hoops, in other words, keeps getting wider. Now, according to our acceleration equations, a rolling ball with a constant acceleration will ring the bells at equal time intervals. As the distances between the hoops widens, so the speed of the ball also increases. Galileo could not measure very short times accurately, but anyone who has any musical training, as Galileo certainly did from his father, knows that the human ear can detect rhythm very precisely. So when we hear the bells ring with a fixed, steady beat, despite the fact that the hoops get farther and farther apart, we are actually making a very precise test of the hypothesis that the ball has constant acceleration as it moves down the track. The equations and the experiment make a beautiful music together. And this brings us to the second part of Galileo's discovery about gravity, that the acceleration of gravity is the same for all objects. So Galileo is credited with a famous experiment, dropping objects from the campanella of the cathedral in Pisa, the famous Leaning Tower of Pisa. Well, did Galileo actually do this experiment? Maybe not. The story is generally thought to be apocryphal. But Galileo did live in Pisa when he first began thinking about gravity, and he describes something much like this experiment in one of his books. So imagine we drop 2 cannonballs, one weighing 100 pounds and one weighing half a pound, which is a pretty alarming thing to do. Newton's apple is tame by comparison. And our observation is that these hit the ground at almost exactly the same time. Galileo says that the big cannonball leads by no more than a few inches. So what conclusion can we draw? Aristotle, who says that the big cannonball should fall 200 times faster, is utterly wrong. Galileo, who says both cannonballs should fall at the same rate, is almost right. And his explanation of the tiny difference is that gravity is not the only force acting. The cannonballs are not quite in free fall. There's also air resistance, and this affects the smaller ball more strongly. So take an extreme case, a feather and a hammer. The feather falls slower. But in the absence of air, says Galileo, those two objects would fall the same. So let's return for a minute to Felix Baumgartner and his record-setting jump from a balloon 39 kilometers above the Earth. At first, after he jumps, Baumgartner is in free fall. After 1 second, he is traveling 10 meters per second, having fallen 5 meters. After 2 seconds, he is traveling 20 meters per second, having fallen 20 meters since the start. After 3 seconds, he is traveling 30 meters per second, having fallen 45 meters. After 4 seconds, he is traveling 40 meters per second, having fallen 80 meters. And all of these agree perfectly with our equations for free fall. But pretty soon, after less than a minute, he stops falling any more rapidly. He is no longer accelerating. In fact, he begins to slow down a little. Why? Is he defying the law of free fall? No. The reason Baumgartner does not continue to accelerate is that another force has begun to be important: air drag. Once Baumgartner is going fast enough, the friction of the air prevents any further speed up. And this maximum speed is called his terminal velocity. Terminal velocity depends on mass and shape and air density. And in Baumgartner's case, his maximum speed is over 375 meters per second. That's faster than the speed of sound. As he falls through denser and denser air, though, that terminal velocity actually gets less. Now, on Earth, at the surface, the terminal velocity of a falling human body is still pretty fast. That's why you need a parachute to slow the terminal velocity even more. But on a planet with a much denser atmosphere, the terminal velocity might be a lot slower. You might not need a parachute to land safely. I once wrote a science fiction story set on the planet Venus. The atmosphere there is more than 50 times denser than on Earth. And the hero of my story finds it necessary to skydive without a parachute from an altitude of more than 70 kilometers above the surface of the planet, even higher than Felix Baumgartner. And it is just possible, just barely, for my hero to survive because the terminal velocity is so much slower in the dense atmosphere of Venus. But with no atmosphere, as Galileo said, a falling body continues to accelerate, and everything continues to accelerate the same. Of course, Galileo could not actually do an experiment without air. But in 1971, the Apollo 15 mission spent a few days exploring the moon. The moon, of course, has no appreciable air. So on the last day on the moon, Dave Scott, the mission commander, performed what has to be the coolest physics classroom demonstration in history.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
It is too bad Galileo could not do his experiments on the moon. Well, there are two things to note about this. First, on the moon, the acceleration of gravity is not the same as on Earth. It's about 1/6 as great. And in Lecture 4, we'll find out why. Two, in the absence of air resistance, the feather and the hammer really do fall just the same. Galileo had it exactly right. So all objects behave the same in free fall. It's a basic fact about gravity. In fact, the law of free fall contains a secret message that won't be decoded for 300 years until Albert Einstein realizes that it is the key to everything. Galileo's first two great discoveries, the principle of inertia and the law of free fall, were terrific. And then from them came the third great discovery, the principle of relativity. Now, we associate the theory of relativity with Einstein, but the original insight belongs to Galileo. Think about the Copernican theory for a moment. In that theory, the Earth is moving at tremendous speed. It's orbiting the sun. It's rotating on its axis. And one objection to the theory is that if we were zooming through space at such a high speed, surely we'd feel that motion. But Galileo says, actually, we would not feel a thing. Imagine a ship at sea. Climb up to the top of the mast and drop a ball down to the deck. Now, Aristotle said, when dropped, the ball moves toward the center of the Earth, straight toward the center of the Earth. So if the ship is at rest, the ball falls straight down next to the mast. But on a moving ship, as the ball falls down, the ship moves forward, so the ball hits the deck at a point behind the mast toward the stern. So Aristotle says that if the Earth were moving so fast, any object not actually tied to the Earth should lag behind it. The object would appear to be snatched backward with great speed. And this is one argument that the ancients made, that the Earth itself had to be at rest. Galileo says it doesn't work that way. So if we think about the ship and the ball has inertia like anything else. Initially, the ball is moving forward with the ship, and it continues to move forward as it falls down. Seen from the sea, it therefore follows a curved path downward. Seen from the ship, it still falls straight down next to the mast. Oh, and by the way, in this analysis, Galileo is solving an interesting physics problem, the problem of projectile motion. If you launch a projectile with some initial velocity, the horizontal velocity remains constant because of inertia, and the vertical velocity changes due to constant acceleration of gravity. And the net result is a parabolic path through space, a path that can be described mathematically. In effect, Galileo has invented the science of ballistics. But back to our story. Just to avoid confusion, let's move everything indoors where there's no wind. We're going to build a laboratory in a cabin below decks on the ship and perform various experiments in it. So can we tell from those experiments whether or not the ship is moving? And the answer is no. Everything in the lab is initially moving along with the ship. Everything in the lab has the property of inertia, so it will continue moving in the same way. So Galileo envisions many possible experiments. He imagines bugs flying around the laboratory, or fish swimming in a fishbowl. He imagines water dripping from a bottle into a basin. He imagines two people tossing a ball back and forth in the cabin. Every experiment will have exactly the same results for either a ship at rest or a ship moving smoothly across the sea. Galileo's insight has some remarkable implications. First, he says that no experiment inside the lab can determine whether or not that lab is moving or at rest. And thus, no experiment here on Earth can detect uniform motion of the Earth through space. In effect, we are all living in Galileo's ship. And finally, absolute motion cannot be observed. Only relative motion can be observed. And that's why this came to be called the principle of relativity. Now, once again, Galileo's discovery contains a hint of things to come, a secret message about the laws of nature that Einstein will later decode. We have discussed three great discoveries of Galileo: the principle of inertia, the law of free fall, and the principle of relativity. And these are all directly related to our everyday experience, but they are facts with profound implications. And they are the basis for everything that comes later in the science of gravity. But remember, gravity is both about phenomena here on Earth and also phenomena in the heavens. So our next step will be to take a deeper look at the heavens. In the next lecture, we will turn to breakthroughs by Galileo's brilliant contemporary, Johannes Kepler. It was Kepler's ability to combine painstaking observations with his own mathematical genius that made possible the discovery of three laws that govern the motions of the planets, and also provided important clues to the mysterious force that steers the stars in their courses.